All right, so you can hear me now? Okay, so this is more or less where I left off yesterday. All right, so I want to talk, I spoke about this yesterday or the day before when I spoke about the difference between alkane plus O2 and alkene plus O2. And I said if you're abstracting an allylic hydrogen atom, that you estimate the activation energy for that reaction in the same way as for an alkane. It's just delta H of reaction, okay? But the frequency factor, you decrease it by an order of magnitude, okay? So, and this is just maybe building on that, okay? So the addition of the double bond in alkene molecules presents additional complexity, okay? Hydrogen atom abstraction from the beta position, so in the double bond results in electron delocalization in the merging alkenyl radical. So in this case, it's this bond is beta. Well, it's actually what we're talking about is this position here and here. We have allylic hydrogen atoms, and both of these are secondary in this case. Okay, here it will be primary allylic, and here it will be tertiary allylic. All right. So when you make that radical, then it's resonantly stabilized. And so typically we don't write it with the double bond here, an electron here, or a double bond here, an electron here. We write it as a single bond and then a dashed line all around. Okay, and that would be a more normal modern representation, so that the electron density is delocalized across the three atoms, all right, and the two bonds, if you want to call it that. So this then, because this happens when you abstract a hydrogen atom and the allylic hydrogen atoms, that makes them about between 13 and 15 kilocalories per mole more easy to abstract. The bond association energy is lower by that amount, and that lowers the activation energy. Okay. Now, sorry, I shouldn't say that it doesn't lower. It lowers the activation energy, but not by 15 kilocalories per mole. The bond association energy is lower by that amount. But remember, you have to use the Evans-Polyani relationship between activation energy and delta H of reaction. Okay, I showed you that yesterday. And so there'll be a relationship between the activation energy for abstraction and the activation energy. That relationship varies depending on the atom that's abstracting. So H, methyl, HO2, and so on. It varies. But in all cases, the activation energy will be lower, right? And will be linearly dependent on the delta H of reaction. All right. I hope you follow what I'm saying. Okay, so, and then the frequency factor is lower. Okay, so once you form, okay, so I that's just filling out what I said yesterday and adding a little bit to it. But what I want to say here is then, okay, so you have an allylic radical. What happens then, right? And allylic radicals are news, either bad or good. I was going to say bad news, or I don't know, but they do have an influence on the reactivity of the system. And typically they will slow down the rate of oxidation because they're resonantly stabilized and they're long-lived. They're not short-lived radicals, right? And so here we have allyl radical. And in our mechanism, and this was studied, I can't remember exactly, maybe it was Judith Zador, I'm not quite sure. But anyway, we have in our mechanism rate constants where allyl plus HO2 was studied, okay? And typically what happens with these radicals, particularly when we have low temperature mechanisms, or we're included in our mechanisms, what we have is allyl plus HO2 gives allyloxy plus OH, right? So the oxygen atom comes in and then you form this radical. And that radical then will be a decision to give you, in this case, vinyl plus formaldehyde, right? And typically you get formaldehyde and whatever other radical because there might be an R here. Okay, in this case, it's just 2 hydrogen atoms, but you could have any kind of a chain. All right. So here, for instance, here's another one. We have this. This is 1-butene 3-il radical. That undergoes reaction with HO2 to give this allyloxy, okay, plus OH, and then again that beta scissions to give you vinyl plus acetaldehyde. Okay, and then here's another one. If you look at it on the other side, okay, and you have to consider both options in the case of the resonantly stabilized radical. So that will give you this radical, which will then give you the C3H5 S plus formaldehyde. Okay, it's just this radical plus formaldehyde. Okay, and so as a product of, we would write, there'll be 2 reactions then. We would have this radical plus HO2 giving this product set and that same radical, because the radical is not, it's neither this or this. It's the resonance structure in between. Okay, but that resonance structure can lead to the formation of this set of products or this set of products. Okay, is that all right with everybody? So I'm just drawing it that way, and probably I should just draw it as the resonance structure in the first place. All right. So inserting a double bond changes the reactivity of the 4 atoms in the carbon chain. So here we have a double bond in the middle of this chain, and so we have secondary vinylic carbon or hydrogen atoms bonded to these carbon atoms, and then we have allylic hydrogen atoms on the carbons next to it, and then we have the typical secondary in the chain. All right. So the allylic CH bond sites are weaker than most others, and therefore they're preferentially abstracted by radicals. O2 is also very weakly bound at allylic sites and fall off rapidly, inhibiting low temperature reactivity. So I spoke about this the other day. I already went through this, where the well depth, if we look at this R plus O2 giving you RO2 well depth, for a typical secondary species, here a typical well depth between going from R plus O2 going to RO2 is 36 kilocalories per mole. But in the case of the allylic radical, and then you get this allylic peroxy radical, the well depth is only at most 19.7. Okay, so again, there's that, 17 kilocalorie per mole difference in well depth. Okay, so that means that equilibrium, R plus O2 going to RO2, will be more on the R plus O2 side by that amount, right? And hence you won't get very much RO2, you won't get very much chain branching, QH and O2 QH and so on. Okay, and I showed you that plot the other day. So, and then this was a nice study that was published by Mark O'Mell. He worked with Eliseo Ranzi and the group in the Politecnico di Milano. And the experimental data came from Guillaume Van Hove in France, published in 2005. And here's the model prediction of that data. And what we see here is, it's really cool. Ignition delay time here as a function of temperature. And you can see 1-hexene is quite reactive, right? 2-hexene is considerably less reactive, and 3-hexene is considerably less reactive than the other 2. Okay, and there's actually there's some NTC behavior. You could say it was very little, but it's washed out considerably. But there is some NTC behavior for 1-hexene. You don't see any for 2-hexene, and it's completely gone for 3-hexene. But so what happens here is, of course, you've got secondary allylic for 1-hexene. But you can still, if you look on this side of the molecule, say we abstract a hydrogen atom from this carbon here. That's a typical secondary hydrogen atom. We can add to O2, And then we can go through a 6-membered ring and go to branching from this species, some from this and some from this, okay? Whereas if we have 2-hexene, now we have 2 allylic sites in the molecule. Primary allylic on the left here at carbon 1, and then secondary allylic here at carbon 4. So now there's less scope for the low temperature branching chemistry to manifest itself, okay, as for 2-hexene. And then 3-hexene is the worst. So here now we have the secondary allylic either side of the center, okay? We have the secondary allylic here and here. And again, you can form the radical, it will add to O2, and then you'll get RO2. But the equilibrium is going to be very much to the left. And the concentration of RO2 going to QOH, O2QOH, and onto branching will be very low, okay? And because you have it on the 2 sites here, and then say you abstract on the primary side here, well, the rate constants for abstraction at the primary site are going to be lower than for abstraction at the secondary sites. Why? Because the CH bonds at the primary site are higher by about 3 kilocalories per mole. Sorry, the bond dissociation energy, is 3 kilocalories per mole higher. So the rate constants, the activation energies for abstractions are going to be higher by about 1 kilocalorie per mole or 2, depending on, again, on the radical. I showed you tables yesterday of the activation energies comparing primary, secondary, and tertiary. But the chain length here and the 5, 6, 7-membered rings that you need to go to branching won't happen very much for 3-hexene. You have an opportunity because of this structure here for 2-hexene and much more of an opportunity for 1-hexene. Hence 1-hexene is much faster than 2-hexene, and 3-hexene is very, very unreactive in comparison. It's probably the worst case scenario, right? Because you don't have much scope for low temperature branching to occur. I hope that's clear. Okay, this is just a slide I added based on some recent work that we were doing. And it's just showing, look, in alkanes, we have the typical chemistry that happens. So we have abstraction of the fuel, we get the alkyl radical, it adds to O2, we get RO2, and RO2 can go directly to olefin plus HO2 or go on to give hydroperoxy alkyl radicals. And then that can add to O2 and give you chain branching, okay? But if we start with an alkene, right, what gives, alkenes are less reactive, as I showed you here in this slide. So here we have 1-hexene, and here we have N-hexane. And N-hexane is much more reactive than 1-hexene, right? So why is that? Why are they less reactive? Well, because of the allylic structure. But also, you're starting here. So what happens is you do eventually form OH radicals, and then you eventually get HO2 radicals. And then what happens is olefin plus HO2 starts to happen to give you the hydroperoxy alkyl radical, right? And then that hydroperoxy alkyl radical, a large part of it actually ends up to give you forming cyclic ether. So the olefin activation actually seems to occur largely through olefin plus HO2 giving cyclic ether plus OH, okay? So that's just something that we were looking at recently. And you can see here in this sensitivity analysis for 2-pentene. So this is performed at 800 Kelvin and 30 bar, where 20% of the 2-pentene is consumed. And what you see here is that 2-pentene is reacting with HO2 to give this hydroperoxy alkyl radical, the OH on carbon 3 and the radical site at carbon 2. Okay, that's what that 3,2 means. Okay, and here there's another one that also increases reactivity, which is the similar reaction giving you the hydroperoxy alkyl radical, but it's on the 2,3 site. So the OH is on carbon 2, the radical site on number 3. And then what you see is that, where are they? Sorry. I'm trying to see where they are. Okay, where's the 2, 3? Sorry, that enhances reactivity, because now this can add to O2 again and then go to chain branching. Okay, so this reaction of the olefin plus HO2 giving you the QOH starts the chain and makes it available to go to chain branching. Okay, so they're important reactions in activating the olefin chemistry. Okay, I spoke about you have this vinylic system in the center of this chain here, and then, sorry, you've got 2 carbon atoms. If you have the double bond here, you've got one vinylic hydrogen atom here and one vinylic hydrogen atom here too. And then you have allylic hydrogen atoms, right? But what if you have 2 double bonds in the molecule? And you can have molecules like this, where you have 2 double bonds separated by 2 single bonds in the center, right? And so this carbon atom is allylic due to this CC double bond on this side, but it's equally allylic due to the CC double bond on this side. So this is what we call a prime or a super allylic site, okay? Because it's getting resonance from both sides. And so the CH bonds here are even weaker than there would be for a conventional allylic site, okay? By how much I can't remember off the top of my head, right? But they are they're even weaker, okay? So so I have a synopsis here. Kinetic mechanisms for ever larger fuel molecules are being developed due to the increasing computational ability. There's been a lot of focus, in my opinion, on accurate thermochemistry, and the active thermochemicals is a good start, but we need more heats of formation, more than heats of formation. We need entropy, and we need Gibbs free energy, all right? Experimental measurements and accurate quantum chemistry calculations of important reactions involved in the C0 to C4 system are vital for accurate predictions of all fuels, okay? Not just larger ones, but all, and not just the fuels themselves, but the larger ones too. And rate rules are useful for building mechanisms for large molecular weight fuels. Okay, so that's just finishing what I was hoping to get finished yesterday. All right, so now I'll move on to today's material, or what I had intended to do today. Okay. All right, so I had been talking yesterday largely about high temperature chemistry, unimolecular fuel decomposition. Where do we get the rate constants from that? Hydrogen atom abstraction from the fuel, right? Alkyl radical beta scission, and we look at that in the reverse direction. So where do we go next? Okay, and I spoke a bit about the alkene and then the allylic radical, and then how we consume the allylic radicals. One thing I didn't say, and I should have said it in the allylic radical. So I wrote it as allyl plus HO2 gives allyloxy plus OH. Okay, at high pressure, allyl plus HO2 can give you the stabilized adduct, which will be the allyl hydroperoxide. And then that can beta scission the OO bond to give you allyloxy plus OH. But at higher pressure, more and more of that will stabilize to give you the stable allyl hydroperoxide, if that makes sense, right? So just to bear that in mind. So at low temperatures, as I said, we have these then traditional additional 16 reaction classes, which gave us 25 reaction classes. So it involves allyl radical addition to O2, R plus O2. And then the reactions of RO2, one of the most important ones will be alkyl peroxy radical isomerization to hydroperoxy alkyl radical, QOH. Okay, and then the reactions of the QOH, giving you cyclic ether, olefin plus HO2, and then going on to give you chain branching. Okay, and so they're all part of the low temperature class. Okay, and that was for alkanes. So as I was saying in the on Wednesday in the question session, okay, when I was in Livermore, Charlie was very kind and allowed me to study other fuels too and other things. And one of the things I looked at there was dimethyl ether, because I went to the Combustion Symposium in Naples in 1996, and there was work presented on dimethyl ether by Ulrich Fall who presented it. And it showed ignition delay times for dimethyl ether, which showed negative temperature coefficient behavior. Okay, and so we saw the same sort of reactivity as observed in alkanes, right? And so I wanted to then look at that fuel, because if you see here, we have dimethyl ether undergoes H-atom abstraction, and we get just one radical. You see that the methyl group on this side and the methyl group on this side are the same, right? But they have the same environment, right? So we get just one alkyl radical from dimethyl ether. And then at high temperature, that can beta fission to give formaldehyde plus methyl, okay? So as I was saying yesterday then, H-atom abstraction from dimethyl ether by CH3O2 is going to be important for this fuel, because you get lots of methyl from its beta fission, right? But the alkyl radical, or the dimethyl ether radical in this case, right? It's not an alkane anymore, okay? But the radical can add to O2 to give the the RO2 radical. In this case, dimethyl ether peroxy, okay? And then that can isomerize to give the QOH, the hydroperoxy alkyl radical, or hydroperoxy CH2O radical. And that can beta fission so there's no cyclic ether actually that forms here. It can beta fission to give two formaldehyde molecules and OH. So that's the propagation channel that can happen. Or this radical, the QOH, can add to O2 again and give you the O2 QOH that can isomerize to give this radical, which quickly undergoes decomposition to give the carbonyl hydroperoxide equivalent plus OH. And the carbonyl hydroperoxide equivalent can then break this OO bond to give the carbonyl alkoxy radical equivalent plus OH. So again, from one fuel radical, we get 1, 2, 3 reactive radicals, and we have chain branching, like we have in an alkane. And actually, we can apply the same rules and the same reasoning to dimethyl ether as we can to alkanes. So even though, and that's the point of the slide, even though dimethyl ether has an oxygen atom in there, it's no longer an alkane. The chemistry is pretty much the same, right? We form a radical, we can add to O2, we can abstract the hydrogen atom on the other side of the molecule, generating the QOH, then that can add to O2, and we can go through and get the branching, just like you do in an alkane, okay? And that's really just the point of that slide, okay? And then there are some products formed, okay, further down, okay? And then we do this, or we can take rate constants by correlating between structure and reactivity. So there were some studies done by Sehetchian in 1992 and other ones too, which calculate the rate constants for the decomposition of hydroperoxides. Okay, and here they measured the rate constant for this one to be 4 times 10 to the 15 with an activation energy 42.5 all over RT. This is calories per mole, all right? And we use a rate constant similar to this in our mechanisms for the carbonyl hydroperoxide decomposition. Okay, so that's where we take that from. And then I'm just kind of quickly recapping. I showed you this yesterday as well, where we had the rule for RO2 to QOH isomerization, and I had tabulated this in 2002. So we have a 5-membered ring involving the transition of a primary hydrogen atom, secondary or tertiary, 6-membered ring, primary, secondary, tertiary, 7-membered ring, primary, secondary, tertiary. And we can have an 8-membered ring too, but actually by the time you get to an 8-membered ring, those are not competitive because the frequency factor is so low that really the 5, 6, and 7 are the ones that we need to consider in the mechanism. Okay? Sometimes they're important when other options aren't available. So the odd time they are, but generally they're not important, right? And then I had referenced this paper where Stephanie Villano had looked at this system, and then she had correlated all the primary, secondary, and tertiary for 5, 6-membered rings, and then we have a new table of ray constants, okay, which are now based on quantum chemistry calculations, and they're a lot more reliable than what I had done, okay. So, but actually, when we take those ray constants and we compare them with what I had, what we see is actually that they're parallel, but her calculations, or the calculations by Villano and Dean, are 49 times bigger than the ones that I was using in my mechanism, okay? And that's not good, because maybe a factor of 2 difference would be acceptable, or, but a factor of 40 is enormous, right? So I was worried about that, and I said this at the start, so I want, in one of the earlier lectures, so now I want to go through and just explain maybe where I thought we were, how badly off we were. So I was talking about how I published the N-heptane and isooctane mechanisms in 1998, 2002. And I had that table of ray constants in 2002 for the isooctane mechanism. But if you see the difference in ray constant that I was using with what is calculated, that's a factor of 40. Okay, so I wanted to put in the calculated ray constants into the mechanism and then see what effect that had on our predictions, right? So I'm going to show you what happened and how the chemistry evolved, okay? So, and the people that did the work actually were John Bugler, first of all Emma Silk, then John Bugler, and then Q-Wen Zhang, okay? So you can see the work that they did, okay? So this is the general scheme for reactivity, and sorry, at the time. Let me go back. So we had no reaction, for instance, in the mechanism where the RO2 went directly to olefin plus HO2, right? That was in the mechanism published in 2002. And then we had these ones, okay? But we didn't have, and I'm going to, so for instance, if you think we generate the alkyl radical, that adds to O2, we get RO2, and that can give you olefin plus HO2, right? Or it can isomerize to hydroperoxy alkyl radical and then go on to branching. Well, in our previous mechanism, all we had then was the O2QOH going to, well, we didn't even write this radical, and then it went directly to carbonyl hydroperoxide plus OH. And then the carbonyl hydroperoxide decomposed to a carbonyl alkoxy radical plus OH. Is that all right? So this wasn't present in the mechanism, and we just had the system going directly here. But why shouldn't we include, this is like an alkyl radical. And so we should include this O2QOH species going directly to olefin plus HO2 as a reaction class to mimic that of RO2, because it's essentially like an alkyl radical, an alkyl peroxy radical. Okay? It just happens to have an OOH on it. That's the only difference. But otherwise, it's an RO2. Okay? This then can produce an equivalent QOH, but it's actually a double OOH. There's 2 OOHs on it, but it has the radical site on the carbon, which is bonded to the OOH. And then that can produce a cyclic ether plus OH and beta scission products, in addition to producing carbonyl hydroperoxide. So I'll show you an example of what I'm talking about. Okay, so we needed to add these reaction classes then to account for that chemistry and be consistent in the mechanism. Okay, because if you're leaving out potential reaction classes in the mechanism, it's not complete, and you don't fully understand whether you understand the chemistry or not, right? So here is a conventional chemistry that we had in the mechanism. So this is our O2-QOH species. So we had the QOH, so we had formed this radical, and then through a 7-membered transition state ring, we only allowed the hydrogen atom that's bonded to this carbon, right? We only allowed that one to form this, what we call the keto hydroperoxide. I'm calling it doesn't necessarily, it is a ketone in this case, but sometimes it can be an aldehyde too, okay? So that's why I call it a carbonyl hydroperoxide in general, right? But in this case, it is a keto hydroperoxide plus OH. So that's what we had in the mechanism, right? But you see here, why can't this OO abstract a hydrogen atom here? It can, right? Or what about abstracting this hydrogen atom or one of the hydrogen atoms from here? They can happen too. And we didn't include them in the mechanism. If we don't include them in the mechanism, then it's incomplete. And we're not permitting all the chemistry to occur that can occur. And so we're kind of fooling ourselves into thinking that we understand all the chemistry fully. Okay? So the idea was to go back and put everything in, right? So now we say, okay, well, there is a hydrogen atom here. There's 2 of them actually. So through a 6-member transition state ring, and what do we know about 6-membered rings? Are they faster or slower than 7-membered rings in being formed? Is the rate constant through a 6-membered ring faster or slower than a 7? And is it faster and slower than a 5? Or did I say so? Pardon?
Faster.
Okay.
I mean, that's the most stable structure.
Which?
6-membered ring is the most stable structure.
Yeah, well, it's the fastest. So for 5-membered rings, we have the highest frequency factor, but also we have the highest activation energies. So typically, the 5-membered rings start to become important in the middle of the NTC region, and they contribute most to the negative temperature coefficient behavior. So after you reach the peak in reactivity, we'll say at 700, 750 Kelvin, then that activation energy barrier going from RO2 directly to olefin plus HO2, that 5-membered ring one, starts to kick in, right? Okay, the 6-membered rings are going from about 600 Kelvin on, and they're the fastest of all the 3. We'll say, if we consider 5, 6, and 7. Okay, but the 7-membered rings then do happen, but and particularly at lower temperature, right? Where the activation energy is about a little bit lower than the 6-membered ring, but from those you get cyclic ethers. Okay, so they don't typically go to branching. So the nice thing is 6-membered rings are fast, relatively, and they go to chain branching, right? So this one should compete very favorably with abstraction of this hydrogen atom here to form this radical. And once this radical is formed, we can now get this olefinic hydroperoxide plus HO2. Okay, or this can give you a cyclic ether plus OH, which will then go on to give you. So we added these reaction classes 26, 29, and 27 to the mechanism to make the chemistry more complete. Okay, so when we did that, okay, so in all the graphs that I'm going to show you now, right, this is for N-heptane oxidation, 5-1, 13.5 atmospheres. The symbols are the experimental results. The black line was the previous model prediction. Okay, so the black line here is our initial model prediction. You can see that it's capturing it reasonably well. We're still a bit slow here by probably a factor of 2 or more at low temperature, but we're getting the behavior mostly right. Okay, but when we add these alternative reaction classes and the isomerizations, it gets too slow at lower temperature and too fast or faster at higher temperature. It's actually fitting the data much better at higher temperature. But it's way too slow at lower temperature. Why? Because at lower temperature, this channel is producing a molecule plus HO2, okay? And we're getting a molecule plus OH, but we're not getting, well, this will give you, so they're largely, what's happening is we're largely getting these stable molecules plus HO2. And at low temperature, HO2 won't give you any branching because it will abstract from the fuel to give you H2O2. But it isn't until it gets to about 850 Kelvin that that OO bond can break and it starts to produce OH radicals. All right? So that's why it inhibits reactivity at lower temperature. And then once you get beyond the 850 mark, it starts to increase reactivity. Okay, and that explains it very easily there. Okay, so it's that HO2 that's being formed that is not going anywhere because it'll give you H2O2. Okay. Okay, so when we added the cyclic ethers then, okay, that did make things a bit faster at lower temperature, but it made things way too fast at higher temperature. Okay, so just adding that reaction, this reaction class gave us the red line, adding the blue reaction class gave us the blue line. And now we're way too fast, and it ain't looking anything like the experimental result, right? And so it's kind of be freaking you out, okay? Because do we understand the chemistry? And the answer is no, right? Very much no, okay? Now there were then measurements or calculations, and the first calculation of this was by Samantha and Green, Bill Green again, looking at RO2 to QOH and O2QH given carbon hydroperoxide plus OH. And they did some ab initio calculations, CBS QB3 level. The rate constants for the isomerization of RO2 to QOH and O2QOH to carbonyl hydroperoxide were 10 times those that I was using, right? So when we put those in, it's getting worse and worse, right? And so I had a lot of compensation of errors. We emitted a lot of chemistry, and we were getting the right answer for all the wrong reasons, right? And here we had a detailed chemical kinetic mechanism supposed to be giving you all the details of the chemistry, and it's complete and utter wrong, right? So not so good. Okay, there are other things we did too. So the hydroperoxy alkyl radical, we can have intramolecular isomerization of one radical to another in the chain here. Okay, so we added those into the mechanism as well. Okay, and actually it made no difference. It stuck on the green line. Okay, so that didn't seem to make any difference to the mechanism. So that was kind of at least something that we hadn't done, that when we did it, it didn't make much difference. And then really it was Tim Barkholz working with Joe Bazzelli. Tim Barkholz worked at Exxon Mobil in New Jersey, okay? And they looked at this, they were really the first really to indicate that this was really important and it should be included in mechanisms. So up to 2003, this direct pathway from RO2 giving you olefin plus HO2 was not included in mechanisms, all right? And they published these rate constants, and this was published in this meeting. When we added that in, it made things slightly better, but not a lot, right? And so we're now here at this purple line, right? Not good, right? Mechanism ain't working. Okay. What am I saying? Okay, and then this was further, there were other rate constants that came out a little bit later. Chitral Nayak, I think he was working with Tony Dean. But so, just to give the background, Tony Dean worked at ExxonMobil before he went to Colorado School of Mines. So they would have been in touch with one another, and that's why he did that calculation at that time. So he also came up with rate constants, and again, it was slightly better again, but not a lot, okay? So that really bothered me, and I said this to you, and I was like, okay, those mechanisms are wrong, they're very wrong, and do we really understand low temperature chemistry at all, right? And can I now go back and put low temperature chemistry on a good footing based on the latest and greatest knowledge that we have, right? So that was the mission when John, so Emma, it was actually Emma Silk that did all this work that we showed that it was all wrong. It was in our thesis, but we never published anything because I didn't have anything to show in terms of improving things, except I knew that the mechanisms needed an overhaul badly, okay? So so I'm going to talk now about updates to the mechanism, and all solid lines in the graphs represent constant volume simulations, first of all. And then in the simulations, the previous mechanism is the black line, the new one is the red line, okay? But it's going to be a progressive evolution of the predictions, all right? And so we added, we updated the kinetics. So we looked at alkyl radical bedecision, and we took the best that there was at the time from 2012. Okay, alkyl radical plus O2 giving RO2, we took those from Miyoshi. So these are reaction classes that existed already in the mechanism. Okay, RO2 giving olefin plus HO2, Stephanie Villano. RO2 to QH, Stephanie Villano. QH giving olefin plus HO2, Stephanie Villano. QH giving cyclic ether plus OH. And we took all of these also to be consistent with the same set of kinetics from the same publication, okay, for consistency, and not be taken some from here and some from there, and we wanted to be consistent in what we did, okay? And then we looked also, then we took, so as I said, this hydroperoxy alkyl radical is just an alkyl radical with an OOH group on it someplace, but essentially, to all intents and purposes, it behaves like an alkyl radical. So why don't we treat that like R plus O2 giving RO2, okay? And it's by analogy, okay? And then we have O2QH, this hydroperoxy alkyl radical forming the carbonyl hydroperoxide plus OH. We took the rate constant by analogy by RO2 to QH. And I'll explain that a little bit later. Okay, so as I said, the rate constants calculated by Stephanie Villano were 40 times faster than ours. Not 10, 40, even worse, right? So, and then we added, we added these channels as well, okay? So they're the ones that I just spoke about a little bit earlier, okay? Where we didn't allow the chemistry to evolve, right? We allowed all options, right? And so, for instance, let's just see here. We have this, what is it? 2-methylbutane, okay? We call it isopentane, okay? That adds to O2, and we get the alkyl peroxy radical. Then can I summarize? So we have a 1, 2, 3, 4, 5, 6-membered transition state ring forming this hydroperoxy alkyl radical, okay? That can add to O2, and we're here, okay? And in the old chemistry, now we're here, right? So we have a 1, 2, 3, 4, 5, 6-membered ring. If we had a hydrogen here, we would abstract it. So what we were only allowing in the old mechanism was when we had this O2QOH species, we would only allow it to abstract the hydrogen atom, which was bound to the carbon, which was also bound to the hydroperoxy group, the OOH group, okay? That was the only one we would allow in there, right? But you should allow them all, right? There are 2 hydrogen atoms here, and there's 3 and 3, 6 equivalent hydrogen atoms here. Allow them to happen and let the chemistry fall wherever it may, right? But at least you're allowing the chemistry to progress in a natural way, and it should be in the mechanism, okay? But before, this wasn't allowed, right? So, but I knew also that the thermochemistry was wrong. And actually, that was a large part of the key to getting things right, right? And this is work that we did in 2015. We've done more recent work working with Stephen Klippenstein, who's done much higher level calculations on the thermochemistry. And we've now re-optimized all the chemistry again, right? But it's going to be a similar story to, a more modern story, but it's a similar story to what I'm going to tell you here. Okay. I showed you this on day one and the importance of the thermochemistry, okay? And I went through it, so I don't want to go through it in any great detail here again. But just to recap on the very first one, the alkyl radical calculated with the new Burke thermochemistry, in general, the Gibbs free energy was lower by about a half a kilocalorie per mole compared to what it used to be. And the Gibbs free energy of the RO2 was 1.4 kilocalories per mole higher than it was before. So that means that well depth is 1.8 kilocalories per mole shallower. That will shift that equilibrium of R plus O2, giving RO2, to the left and leave you at R plus O2, okay? And the rest of it you can see yourself. I already went through it in detail on Monday. But what it's doing is, because of all these arrows going left, it's slowing down the reactivity. Now, you might think that's bad news, right? The thermochemistry is bad news. But if I go back to this plot, yeah, this one, it's actually good news, because before I was using rate constants for these isomerizations, which were 40 times too slow, based on what the calculations were saying. And I had to do that to get the mechanism to fit the data that we had. Why? Because the thermochemistry was wrong. Okay? So don't ever underestimate the importance of the thermochemistry in your calculations, because it can have a big influence on the kinetics, right? A lot of these systems are at equilibrium or close to equilibrium, and therefore the thermochemistry is going to be very important in your predictions, right? So that's what's happening here, right? So the thermochemistry was really important. And so here was an original model prediction. And when we changed just the thermochemistry, the model became so much slower, because it was shifting everything back towards reactants and not onto products, right? And so that was the first thing. Okay. Then we changed the R, giving olefin plus smaller radical ray constants from the Comandini recommendations. Okay. And so the system became slightly faster, but it's only maybe 10% or something. It's not a huge effect. It is different, right? And it does have an influence. And you can see, also look at where it's having the influence. It's actually in the NTC region that's having the influence. So why? Why would R given olefin plus R, if we change those rate constants, only, see, it's not having any influence at high temperature, none at low temperature, but only in here. What happens at low and intermediate temperatures? What happens to R?
It combines with oxygen.
No.
HO2.
No, it adds to O2 to give you RO2, right? And then it goes on to react in the low temperature chemistry, okay? But if you have more R undergoing beta scission, that's going to slow things down in that regime. If you have less R going to beta scission, more of it will add to O2, giving you more RO2, and that will speed things up, right? So what this is saying is that the Commandini rate constants were slightly slower for beta scission than the ones we were using, okay? And hence the system sped up a little bit, okay? But it sped up in this regime where the RO2 chemistry is particularly important, and where they are decompositions not important at all down here. Why? Because the activation energy is too big for it to happen. And so you're not getting any, in this regime here, you're not getting, and at temperatures below this, the R cannot beta scission at all. So it only starts to be able to beta scission here. Okay, now it's, okay, what is inverse temperature 1.6? I don't know, but it's about 600 Kelvin. Okay, and this is 1250 Kelvin, right? What you're looking at here is a very difficult plot to interpret, right? Ignition delay times are very easy to simulate, right? Constant volume, you put in the initial temperature and pressure, and it evolves until you get ignition, right? But actually, to interpret it, it's very difficult because you're plotting the initial temperature, right? But the chemistry starts at 600 Kelvin, but it proceeds through all the temperature range, through the chemistry evolves through the low temperature kinetics, the intermediate temperature kinetics, and the high temperature kinetics before it auto-ignites. And that happens for every point along that curve. So it's actually a very difficult plot to interpret, this plot, right? It's not simple, okay? So just bear that in mind when you're looking at them, okay? But essentially, this difference is coming from the competition between alkyl radical beta scission and alkyl radical addition to O2 to give you RO2, right? Okay, and it's telling you how much that affects it. Okay, now, then if we look at the alkyl radical plus O2 given RO2, that had no effect, okay? Whatever rate constant we were using from before was similar to the Miyoshi rate. Okay, now the RO2 giving olefin plus HO2 rate, okay? We have this model prediction here, and now when we include the rate constants for that, it makes things too slow. Okay, so in other words, the rate constants that Villano and Dean calculated were faster than the ones that we were using. Okay, and so we have more RO2 giving us olefin plus HO2. That's a propagation, and so there's less RO2 available to go to QOH, and that add to O2 and go to chain branching. Okay, and then when we added the RO2 to give isomerizing to QOH, it sped things up considerably, right? And that now it's again approaching the experimental data in the NTC region, but now it's too fast at lower temperatures, right? But and it makes sense that it sped things up because the rate constants calculated by Villano were 40 times faster than ours. Okay, and then if we look at the QOH giving cyclic ether plus OH, it has a slight effect on it. It's making things a little bit faster than what we were using. Okay, and then the QOH giving beta scission products, that the system doesn't seem to be very sensitive to those reactions actually in this example of N-pentane. Okay. If we then look at, again, hydroperoxy alkyl radical adding to O2, okay, what we were using and the rate constant from Miyoshi, this makes things slower, okay, slightly. And you can see we were using this rate, I'm not going to get bogged down on it. Let's leave it, okay. Then if we look at the isomerization, so this is like, these isomerizations are the second isomerization. So we have RO2 giving us QOH, And now we have a second isomerization, which is analogous, which is O2QOH giving us a carbonyl hydroperoxide plus OH. Okay, but do I have a, yeah. So what I'm talking about here is this. Here we have, this is the RO2. So 1, 2, 3, 4, 5, 2 pentyl radical. It adds to O2, you get 2 pentyl peroxy, and that can isomerize to give this hydroperoxy alkyl radical, right? Now, that hydroperoxy alkyl radical, okay, we have an analogous reaction where, again, we have now the hydrogen atom on this carbon. We have an OO group here, and we have an analogous isomerization to what we had for the RO2, okay? Except, you see, this hydrogen is bonded to a carbon, which is bonded to two other carbons. This hydrogen is bonded to a carbon, which is bonded to other carbons, but also an OOH group. What will oxygen atom do to this CH bond? What will it do?
It doesn't weaken?
Yeah. So if we have this carbon, if there's an oxygen bound to it, the oxygen atom draws electron density towards it. It's more electron withdrawing. It's much higher electronegativity, okay? And hence it weakens the CH bond. And so we had this idea that, okay, it weakens it. And so relative to a typical secondary hydrogen atom, it would weaken it by, we would lower the activation energy by 3 kilocalories per mole relative to the RO2QOH isomerization. Okay? So we would take the same Ray constant for this isomerization on a per H atom basis as for this one, and we would take the same expression, but just lower the activation energy by 3 kilocalories per mole. When we did that, the prediction went from the black solid line to the red solid line. So now we're too fast. But it has a big effect, actually, on the reactivity. And why? Because, again, our previous Ray constants for this step were based on an analogy for our previous Ray constants for RO2 giving us QOH. They were 40 times too slow. So now these ones were also 40 times too slow. And hence, this huge jump in reactivity when we made that change, right? And then, okay, so now we make actually a good change, right? So it looks reasonably well, still out by maybe a factor of 2 or more, maybe 3. But it looks better, except here at lower temperatures, way too fast. And what had happened was, do I have it? Okay, I'll write it on the board here quickly. What happened was, for these carbonyl hydroperoxides, so let's say we have this guy. Okay, so this is the keto hydroperoxide, carbonyl hydroperoxide. Okay, to break this bond, we had a Ray constant of 1 times 10 to the 16, 0, and an activation energy of 43 kilocalories per mole, right? But actually, to get good agreement, and to get a good agreement with the experimental results at the low temperature range up to this point here for all fuels, what we had done was we had lowered the activation energy for this OO bond cleavage. We changed it from 43 kilocalories per mole down to 39. Okay, so that was 4 kilocalories per mole too low, right? But we had to do that such that the reactivity that we were predicting at low temperature was fast enough, right? Again, why? Because the thermochemistry was wrong, right? And everything was shifted to reactants, and the system wasn't reactive enough. Now, when we put it back, it is now reactive enough. We're getting the right balance of RO2 going to QOH, the O2 QOH going to carbonyl hydroperoxide, and so on. So now we can put the rate constant back to the right value. So that's what we did. And we got this red line. And now it's looking much more like the experimental result that we measured. But now everything is as per calculated and as best we can in the literature, in the mechanism, which is really nice, right? And it says actually, well, we do know, okay, the chemistry. Then we also added, what we do? Okay, so we said, okay, this O2QOH can go to this radical, and then that radical, okay, and that doesn't make any change. That's just, okay. But then that radical, we didn't have the cyclic ether, so we now added the cyclic ether plus OH from this radical. So this is like a QOH radical, except it has an OOH group on it already, okay? And that makes things slightly faster, but not hugely. And we also allowed an olefin plus HO2 to be formed from this RO2, okay? And that had no effect on the system, okay? So what effect did it have? Okay, so what am I trying to show? I can't remember what I was trying to show there, and I don't have the time to go through it. Okay, so what we have basically, what we had then at the end was a mechanism. Okay, this is just showing sometimes we couldn't take Miyoshi or we couldn't take Sharma. I can't remember exactly, and we had to decide on which rate constants best fit the set of rate constants that we had. Okay, for N-pentane, it didn't matter, but there was a difference in choice for the rate constants if we chose Miyoshi or Sharma. Okay, but in the end, these solid lines are constant volume simulations, but the dashed line here is the simulation including facility effect, okay, of the data. And you can see now that the simulation for both N-pentane and isopentane, including all what we think are better thermochemistry and best known rate constants for the system, match the data very well. And that was really the result of the study. Okay, that's what came out. Okay, I won't go into this. Okay, so we had then good agreement, and you've seen this a couple of times already, for N-pentane, neopentane, and isopentane. I had a discussion with one student on the way to the banquet last night, and we were talking about the octane number of N-pentane, isopentane, and neopentane. And actually, I don't know whether you were told this or not, but N-alkanes typically have octane numbers that are lowest. And then the more highly branched the molecule, the higher the octane number. Okay? But in the case of the pentane isomers, actually neopentane has a lower octane number than isopentane. Okay? And it sort of contradicts conventional wisdom, right? But you can see actually that in this regime, a good measure of octane number is if you look at the reactivity at about 800 Kelvin or 850 Kelvin. And you can see actually neopentane is faster to ignite in that regime compared to isopentane. And it is true actually that the octane number of neopentane is lower than isopentane. Okay? So, and then this is just showing our previous model prediction of jet-stirred reactor data compared to the model predictions with all the updates that we had in there. And the solid line is the updated model, the dashed line is the original model prediction. And you can see that the chemistry is much better now at capturing this too. Okay? And here we also applied these rules to butane, okay, where we had good data. here are data that were taken by Arca Escola, working with Craig Tages for isobutane. These were published in 2013. And we're just showing what is he? He has a normalized signal of, what is it? Ketohydroperoxide formation, experimental versus the new model. And you can see here that the new model is capturing these data for isobutane really well at 3 different conditions of oxygen concentration. Okay? Before, it wasn't able to accurately capture these data. Okay? So that is further evidence that the new rules and our understanding of the low temperature chemistry is much better. Right? And then here are more data for N-pentane. You can see that the lines are going through the points very well. Here's some validation for N-hexane using the same rules. That's good. That was all published. These are jet stirred reactor data taken from by Philippe Degault in Orléans. Here are other N-heptane data with the same rules. And then N-heptane speciation data, again, good. Okay, and then we applied that, as I said, to all the 3 pentane isomers. We published 2 papers on that, and then these rules were then used by Lim Chai and Heinz Pitch to simulate C7, C8 to C11 species, and then developed a mechanism for dodecan that worked. Okay, so you can see that we had a lot of success with that, and we actually have data it was Colin Banyan that took the data for the hexane isomers, which we published. And then he also took data for the heptane isomers, which you haven't published yet, but we hope to publish it this year, actually, finally. Okay, and using the rules. So here are all the data points. I won't go into it, but you can see that N-heptane is the fastest to ignite. And actually, we couldn't measure the ignition delay of N-heptane in this temperature regime here because it's just too fast in the facility. Okay, but you can see that, the 2 and the 3 methyl hexane, the red dots and the blue dots have octane numbers of 42 and 52, which are the lowest, and you can see that they're the fastest to ignite among all of these other species. So you can see that the reactivity is decreasing with increasing octane number, right? What's the magenta is 3-ethyl pentane. Where's 3-ethyl pentane? It's here. It is 65. Okay, and then the least reactive is which one? 2,2-dimethyl pentane, is it? So 2,2-dimethyl pentane is it's 2,2,3 trimethylbutane is the least reactive. And you can see here, we have to go to 20 bar, and you can see that it's so much less reactive than the others, okay? And it's, again, in keeping with the octane number, that's 112, okay? So you can see that when we measure the reactivity of these alkanes in the rapid compression machine, the reactivity does reflect the octane number of the fuel, okay? That's just some more data. Okay, so to conclude the reevaluation of our our understanding of low temperature oxidation of alkanes, for how long was that? I published those papers 98, 2002 to 2015, so about 13 years. I was thinking, do we really understand low temperature chemistry? And I think what I've shown there is we do, actually, and with complete, with good thermochemistry and accurate rate constants, we can actually simulate these fuels now. Okay. So at that, let's take a break.